Okay, here's a follow-on problem to the first class example I have. And what I want to do is look at part B. So, concerned that the estimate was not accurate enough, the school board asked to have the voters sampled again and a new confidence interval computed with the same level of confidence. So we still want 95% confidence, okay, yet we want a smaller margin of error. Okay, this time we want a margin of error of 0.03. Okay, so we want an estimate of some kind. So remember, a confidence interval is an estimate plus or minus a margin of error. And in this case, for proportions, our estimate is p hat plus or minus the margin of error. Okay, so the margin of error, the formula for the margin of error is equal to z star times the square root of, in this case, p hat, q hat. And the reason I say p hat or q hat is because previously we have a p hat, so we have an estimate. So assuming this estimate is reasonably accurate, I think that's 0.46 something. 144 divided by 330. Oh, my bad. 0.36. Okay, so we have an estimate. So assuming that that estimate is close, we can use it here. So what I'm going to do is I'm going to show you the math. You can plug all the numbers in, or you can just solve for n. So what we can do is with 95% confident, I'll do it over here with the numbers. So we want a margin of error of 0.03, and for 95% confidence, our z star is 1.96, and then our estimate of the true proportion, it's the best we have, is this. So I think this is 0.564, and that's all divided by n. Okay, so over here, if I wanted to solve for n, I could square this, and just let me, it's a little bit sloppy, but I'm going to square everything. So that gives me the margin of error squared, z star squared, times q hat, p hat, q hat, all over n. Alright, so then I can just solve for n. I'll multiply both sides by n, and I'll divide by both sides by the margin of error squared. So these cancel. Oh, multiply both sides by n. So here's n. These cancel, so I get n equals z star squared times p hat q hat over the margin of error squared. Okay, so if I did that over here, I would get n equals 1.960 squared times 0.436 times 0.564, all divided by 0.03 squared. Okay, so it's just algebra. And so n becomes, I'll just do it, 1.960 squared times 0.436 0.036 times 0.564 equals divided by 0.03 divided by 0.03, and I get 1049.6. So even if this was 0.2, you would round up, because again, what we want is we want the largest necessary sample, but not any larger. So 1050 samples is what we should take. Okay, so that's how you do this. Now, if for some reason you don't have any information about the population proportion, no estimate, no previous data, no sample data to go off of, so then you're kind of stuck. You have this formula right here. You have this, okay, or this, whatever you want. So what should you plug in? Actually, I'm going to go back to, we have the margin of error equals Z star times QP over N. Okay, so this is 0.03. This is 1.960. So what can we plug in for P and Q? Well, if you do the math, it turns out that the largest number we can get of this product is 0.5 times 0.5. Okay, just knock it down. Just go 0.51 times 0.49, and I think that's going to be 0.2499. And if you keep going, 52 times 0.48, it gets smaller. Okay, so if you think about it, what we're trying to do, it's not real apparent here, but from here it's kind of apparent that the bigger this is in the numerator, the larger the sample we're going to get. So we're just by calculating the sample size necessary, we're being conservative. We don't want to be overly conservative, so it's okay. This is a safe estimate. So again, n's going to be, if I can do this right, n would be 1.960 squared times 0.5 times 0.5 all divided by 0.03 squared, and that's going to be 1.96 squared times 0.25 equals divided by 0.03 divided by 0.03, and so I get n equals 1067.1. So with this calculation, we should take 1068 samples. Okay, so it's a little bit bigger, but not much bigger. Okay, so that's what you do in the event that you don't have any information. Okay, so hope this was helpful. Good luck.